Let's consider this question. The memory unit of the basic computer is to be changed to a new size that is of 65536 cross 16. Due to this change, now the required addresses will be of size 16 bits. The instruction format of a memory reference instruction remains the same for I is equal to 1 with the address part available in bits 0 through 11. For I is equal to 0, the address part of the instruction is available in the next memory word and has a total of 16 bits. Modify the micro operations during time T2, T3, and T4 if necessary to handle this new modified configuration. So let us first understand what changes are to be made to the actual configuration of the basic computer. So previously, the size of the memory you need for the basic computer was 4096 cross 16. As per this updation, the size is 65536 cross 16. That means still the size of each memory word, the storage capacity of each memory word is 16 bits, but now the total number of memory locations are updated. So 65536 is actually 2 raised to 16. So we can represent this memory unit as 2 raised to 16 cross 16. So there are total 2 raised to 16 memory locations and each location is having a storage capacity of 16 bits. Now as there are 2 raised to 16 locations available in the memory, if you want to uniquely identify a location, you need to provide an address of 16 bits. So this information is given in the first part of the question. Now, if we are changing the configuration of the memory, it will directly impact the format of the memory reference instructions. So that is described in the second part of the question. So here it says that the instruction format of a memory reference instruction remains the same for I is equal to 1. I is the MSB, the last bit of an instruction code in the basic computer, and it defines the addressing mode. So if I is equal to 1, that means indirect addressing mode. In that case, you can follow the same instruction code format and the address part will be available in bits 0 through 11. So this is how the instruction code format will look like for any memory reference instruction. The first part will have the address of size 12 bits, bits 0 to 11. The next part would be the opcode, next 3 bits, so 12, 13, and 14. And the last bit, the MSB, would be the addressing mode bit, which will be stored in a flip flop I. So here, if I is 1, then we don't have to change this configuration. Though a memory unit will have 16-bit addresses, 12 bits will be sufficient to specify a valid address in case of an indirect memory reference instruction. So for that, we can follow the same instruction cycle for decoding the instruction as well as for reading the effective address. Now, if I is equal to 0, that is the other possibility, the other possible value for the last bit. So what should happen if I is 0? Direct memory reference instructions. So that is explained here in the third part of the question. So for I is equal to 0, the address part of the instruction is available in the next memory word and has 16 bits. So basically, if I is equal to 0, then the address must be of size 16. There should be 16 bits available for the address part in case of I is equal to 0 direct memory reference instructions. So this is how instructions will be available in the memory. So let's say this is one memory reference instruction available in the memory. The width of this memory unit is now 16 bits. That means 16 bits of data is available in the memory unit. Now, for this instruction, if I is equal to 0, then the address part will be available in the next memory word. So, for such kind of instructions, the conventional format will have only the mode bit and opcode in the first part, and the address part will be empty, because 12-bit addresses are not sufficient if I is equal to 0 as per the given information, and we need to use 16-bit addresses, so you have to store that 16-bit address in the next memory word. So basically, an instruction will occupy two memory words instead of one. First part will specify the addressing mode and opcode, and the second part will specify the address. Modify the micro operations during time T2, T3, and T4 to conform with this configuration. So let us start with T0, because whatever happens in the fetch phase, that will also have some impact on the subsequent phases of the instruction cycle. So let us write the sequence of micro operations for the instruction cycle starting from the first timing signal T0. So at time T0, the content of PC is transferred to AR. This is anyway not required to be changed. It is clearly mentioned in the question. You have to basically modify this logic starting from time T2. At T1, uh, using this address value, the control fetches the required instruction in the IR, and at the same time, PC is incremented by 1. So these two timing signals correspond to the fetch phase. Now, if we talk about the next phase, that is the decode phase, then we have to use the timing signal T2. Now, what usually happens for the basic computers decode phase, whatever instruction is available in IR, the control attempts to interpret the meaning of that instruction. So, IR of 12, 13, and 14. These three bits will be used for the decoding purpose. Based on the actual available value in these three bit positions, the control will determine the instruction given. The last bit of IR, that is IR of 15, goes to I, a designated flip flop that holds the addressing mode value. And originally, in the basic computer, the first 12 bits goes to AR. Now here we cannot directly write IR of 0 to 11 to AR, because now, as per the updated information, we have to consider the addressing mode first. If I is equal to 1, then some task is to be done, some process is required to be followed before transferring the address to AR. And if I is equal to 0, then also some new process is required to be determined to get 16-bit addresses in AR. So we cannot actually write this statement as a part of the decode phase T2. So here we have to wait until the instruction is decoded, because the logic to be modified for timing signal T2, T3, or T4 is to be done, it's to be given only for memory reference instructions. If there is any register reference or IO instruction, then no updation should take place. The original sequence of operations will follow to complete the instruction cycle. So at time T3, the control will first identify the type of the instruction. The type of the instruction depends on the output of this decode process. That's why the control has to wait till T3. It has to let the control complete the decoding process to understand what is the output of the decoder. So let's say if D7 is equal to 1. In that case, the given instruction is clearly a register reference or IO instruction. So the control is not required to modify anything. So in that case, continue with the original sequence. But if d7 is not equal to 1, in that case, the control needs to decide what is the addressing mode. Because if d7 is equal to 0, that means it's clearly a memory reference instruction. So in this case, the control has to next identify the mode of addressing. So after having this condition as true, the control will check for the addressing mode. So if I is found to be 1, that means indirect addressing. In that case, what the control needs to do, whatever is available in the address part, that should be treated as the address. So 12 bits are sufficient to uh, use as the address for indirect memory reference instructions. So a here, as we have updated the addresses, the size of AR and PC are also required to be changed. As addresses are of now 16 bits, both these registers should have the capability of storing 16 bits of data. Right? So if we consider this change in the size of AR and PC, then we have to understand that AR will need a 16-bit address value. But as per the information given in the question, the address part of 12 bits is sufficient for AR. That means only first 12 bits will have some value, the actual address value, and the remaining 4 bits can be set to 0 to make a total of 16 bits. So if I is equal to 1, what you need to do? You have to set the last 4 bits of AR. AR is now of size 16 bits. So you have to set 12 to 15 of AR to 0. The remaining bits, the first 12 bits of AR, will receive the address from the instruction code itself. So this is to be done in case of an indirect addressing mode. If I is equal to 0, that indicates a direct addressing mode. So in that case, what is to be done? The address is available in the next memory word. The address part will not have the address. Instead of putting the address in the address part, for direct memory reference instructions, the control will get the address by reading the next memory word. So whatever is available at this address, the control has to fetch that. Now, how the control finds the address of the next memory word? So, for that, you can use PC. Initially, when the instruction execution starts, the PC points to the instruction itself. Then, during the fetch phase, PC is incremented by 1. So PC is currently having this address. PC is basically pointing to the memory word which is having the address part, the second part of the instruction. So for I is equal to 0, this PC can be transferred to AR. And PC is supposed to point to the next instruction's address which is available here. You can again increment PC by 1, so that it will point to the next instruction in sequence. Now, all this processing will happen during time t3. Still, the control needs to read the required address in AR. Originally, for the basic computer, effective address is required to be read only for indirect memory reference instructions. But now, as we have changed the configuration in both the cases, whether I is equal to 0 or I is equal to 1, you have to read the effective address in AR. So now, for I is equal to 1 or I is equal to 0, you can give a common micro operation for reading the effective address, which is same as the original third phase of the instruction cycle, M of AR to AR. So if I is equal to 1, what value will be available in AR? For last 4 bit zeros and first 12 bits the actual address. From where the control will get this address? From the address part of the instruction. In case of I is equal to 0 direct addressing, the control will get a whole 16-bit address from the memory. So this is the required change to be made to the configuration of the basic computer.